So we're in our penultimate lecture and essentially our final topic. So I'm going to discuss something that I don't exactly know how to title, so I called it Variation of Hilbert Spaces. And let me describe what that is first. Okay? So say X will be some complex in general theory. This is a little too close. So X will be some complex manifold. It'll be Kähler, so let's say G be a Kähler metric. And L will be a holomorphic line bundle. So we're going to stick with using line bundles in this setting. You can also use vector bundles, but it's more complicated and it's not developed yet. Good. So with this, I can define, and maybe let's let so e to the minus phi be a metric for L. So this, I'm now using the notation I introduced yesterday. It's the same as the notation H, if you want. Okay? So the notation is there because the curvature would be dd bar phi. Okay, so then we can define for this data the Hilbert space of holomorphic sections, which are L2. So it's a set of all f, gamma O of xl, such that the integral f squared e to the minus phi dv sub g is finite. Okay, so this is a holomorphic, a Hilbert space of holomorphic functions. Later we'll also look at Hilbert spaces of sections that are not holomorphic. Okay, so this is the model for a single space, but now suppose you want to somehow vary the metric. Okay, so we want to do this in a particular way that may seem strange at first, but later you'll see why I'm doing this. So the parameters of this variation will lie in some domain omega and Cn. And later on, we're even going to take omega to just be a disk in C. Okay. So what does it mean to have a variation of metrics? Well, it's a family of metrics depending on a variable in omega. So you could define that directly, but I'm going to do something which, as I said, looks a little strange, but later you'll see why. So here's the definition. A family of metrics for L is a metric for the line bundle maybe say over omega, put that in brackets. So is a metric for the line bundle. Okay, so I'm just going to write it down and explain what it is. So it's a metric for the line bundle, which is the pullback of L by the projection to the first factor. This P1 from x cross omega to x is the standard projection to the factor. So let me just remind you, what's a pullback of this? So you have L is over x. What's the pullback of L? It's the set of all points of this new space. So let's say that's xt, comma, a vector v, such that v is in, v is in the fiber over p1 of x and t, which is just Lx. Okay, so if you look at the fiber over point xt, it's exactly the fiber of L over x. So there's a natural isomorphism This is naturally isomorphic to L sub x. And sometimes I'm going to call this isomorphism I sub t. Okay? So as I said, this looks like a convoluted way of saying you have a family of metrics depending on a parameter, but you will see why I choose to use this. So. Okay, so with this isomorphism, the metric e to the minus phi I1 pullback of L to x cross omega defines metrics e to the, and I'm going to call e to the minus phi sub t, which are just, so if you take I sub t and apply it to the metric e to the minus, the induced isomorphism applied to the metric e to the minus phi. In other words, you're just taking this metric and restricting it to the fiber, restricted to the fiber over. This is unfortunate. It looks complicated. It's really not very complicated. So if you want to just think for now that you have a family of metrics depending on a parameter t and omega, that's fine. That's the picture.
So
yeah.
for a trivial open setting x, what this means is that phi is a function of two things, t and the coordinate around the fiber.
Yes.
T is having with the omega.
Yes. Yes. Okay. So now, if you given this family of metrics, to the minus phi, we can define a family of Hilbert spaces. So you just take this induced metric for the line bundle L, and you define it in exactly this same way. So now for every point t and omega, you have a Hilbert space of holomorphic sections of x with the metric e to the minus phi t. So then we get a fibration, let's call it h phi to omega, okay, whose fiber over t in omega is simply, so the fiber of a fibration is usually denoted like this, and this is just the Hilbert space we called phi t. So I'm just changing notation to put the t outside to indicate that I'm a fiber of some bundle. Okay. So the first question you can ask about this fibration is it locally trivial? So, question. So is this fibration locally or not locally trivial? So you have a family of Hilbert spaces and you want to know whether or not, there's no topology yet, so it's complicated to even discuss this question. But one thing's for sure, it would be trivial if all the fibers were, in some way, you could say in a canonical way, the same Hilbert space. So in general, the answer is no. So So I'll give an example. Suppose we take, so x equal to Cn, L is the trivial bundle, and the family of metrics will be e to the minus mod t squared z squared. Let's put x. X is a point in Cn. This is your metric. And the Kähler metric will just be the Euclidean metric. Dx squared. And so these Hilbert spaces will be the set, so let's see, H of phi sub t will be the set of all entire holomorphic functions such that the integral of f squared e to the minus mod t squared on x squared, f of x, dv of x is finite. And so this is a collection of Hilbert spaces, all but one of which is infinite dimensional. But one of them is not. Yeah?
Where you define e to the power minus p equal to id, is that there with respect to id?
It's just the induced map, so yeah, I don't care too much. It's not pullback, it would be a push forward if this map goes this way. But yeah, it's just the induced map, the metric induced by this isomorphism. Okay, so here you have an example where you don't have local triviality. So maybe I'll leave this as an exercise. This will be one of my exercises. I didn't come up with enough exercises today, so I'll give one simple one. Okay, so it will be an exercise to show that this h phi to c, so here we can take omega equal to c for simplicity, but you can take it to the cm if you want, it doesn't change anything, is never trivial in a neighborhood of 0 in C. Actually, depending on how you define, so if it were trivial, we would like to define a holomorphic vector bundle with Hilbert space fibers. And so it really depends how you're going to define that. Usually you ask for the inner products to be quasi-isometry. So the Hilbert norms should be equivalent norms in the sense of functional analysis or topology, same thing. And I think that these are not, probably, but I haven't checked that. So. Okay, so we want to avoid this. So this is bad for us. This is bad for us. So we will introduce now hypotheses to force triviality. Okay. So this is going to be our standing assumption. It's that the manifold X is going to be, first of all, it's going to be Stein, so a strongly pseudoconvex manifold, but actually it's going to be a bounded domain inside some other strongly pseudoconvex manifold. Stein. And also, L will be L tilde restricted to X, where L tilde is defined on Y. So the line bundle itself extends up to the boundary. And the metric e to the minus phi, the family of metrics, will be e to the minus phi tilde restricted to X cross omega, where e to the minus phi tilde is defined on, so it's a metric for P1 pullback of L to y cross omega. So I don't care about extending up to the boundary of omega, but I care about extending up to the boundary of x. Okay. And then maybe a final assumption is that maybe this is implicit, so metrics are always smooth. So these are not singular metrics. Okay, so with these hypotheses, this actually implies that the Hilbert space H phi t, right, so this is a subspace of the space of holomorphic sections of L. And the claim is that this subspace is independent of T. Okay? So is as a subspace independent of T. So any holomorphic function which is in H, any holomorphic section in H phi sub T for some T is in H phi sub S for any other S. Yes, yeah, so this already tells you it's smooth up to the boundary. The fact that it restricts to X from a smooth metric in the, so, and maybe I should have said omega also. Or I wrote omega, but I've been saying G, sorry. Okay. It's very common in complex geometry never to talk about the metric, always to talk about the metric form. I almost never use the metric. Okay. Right, so in this sense we have something that can't be misconstrued as anything but a trivial vector bundle. But these hypotheses also imply that this H is always infinite dimensional. So, two dimension of H phi t is infinite, which doesn't happen in this example. Okay.
It's not so much as a bundle of Hilbert space, but the same abstract topological vector space with varying inner products as you do.
But that's what a vector bundle always is. It's locally such a thing always. Right? So that's my point. This is actually a trivial Hilbert bundle with non-trivial metric. So you get that. So H of phi to omega is a trivial Hilbert, so vector bundle, with non-trivial Hermitian metric. But now, because it's infinite dimensional, I have to say a little bit more about the metric. There's a topology of infinite dimensional vector spaces that's actually important. So we upgrade to Hilbert. Okay. So this is a variation of Hilbert spaces. And it's also a vector bundle. So the sorts of things we want to know about this vector bundle is information about its curvature. You have a metric. Okay. It's trivial, so you have a holomorphic structure. And so you can talk about what is the curvature. And we would like to say something about the curvature of this bundle if we know something about the curvature of this metric. Okay. So that's the goal. And it will be, I think, very surprising. It was surprising to me. This is a theorem of Berndsen that I'll be describing. It's very surprising to see the connection. It's very pleasant, and it uses much of the stuff we discussed up till now. Okay, so I mentioned that it's a holomorphic vector bundle simply because it's a product. It's H of phi. If we're calling it trivial, it's H phi sub 0 cross omega. And the projection map is just a projection to omega. But still, I want to describe the holomorphic structure in a more productive way. One can describe the holomorphic structure in a better, more useful way. So I'm going to make this the definition of the holomorphic structure, but it's a theorem to prove that this is a trivial holomorphic vector bundle.
At any rate, the data product is just very conformally from fiber to fiber. If one can use the word conformally, this is
they're quasi-isometric. Yeah, that's what I said. I wouldn't say conformally. That's not correct.
I'm not even sure if one can use the word.
Of course, you can. Conformal just means that it's a function. One inner product is a function times the other. That's not true here.
It's not true.
No. Why should an orthonormal basis for phi sub t stay an orthogonal basis for phi sub s for some s different from t? No, there's no. The answer is no. You can check, but since I have to keep boogieing, if you disagree later, come back and raise an objection. Okay, so so let me describe this holomorphic structure. So definition. So I'm just going to tell you what is a holomorphic section. So a section F of, say, h of phi to omega. It's clear what a section is. It's a map that assigns to every, so maybe I'll just say is an assignment. No, actually, I don't want to do it this way. We'd like to say that it's an assignment to every point in omega of some element in the Hilbert space. But actually, I want to describe it in terms of the geometry of the underlying manifold and weights and so on. So it's going to be is a section, and I will call it F bar to distinguish. So in of this line bundle. This was the point. This is why I introduced this funny notation. So you want a section of this line bundle such that, so the restriction of F to, say, the fiber, so X cross T, is actually in the fiber over T. So it means that it's holomorphic along the fibers of this fibration, but it may vary in a different way with respect to T. Okay? And then you say that this section is holomorphic if this section is holomorphic. So F is, so we'll write it this way, F in gamma of omega h of phi is holomorphic if and only if F bar is holomorphic. It just means that it varies holomorphically with respect to T as well. So it's not just a holomorphic section here, it's also square integrable on the fibers, but that's already contained in this information here. Okay? Right, so the way, the logic of this is that a priori F is in this space, and then the equivalence of the two things is holomorphic is equivalent to this. Okay. So actually, I'm going to be at least as interested in the dual bundle. So if you've got one of these fibers, it's a Hilbert space, so you can certainly look at its dual. Right, this is also a Hilbert space. Well, the norm here, so the norm of, say, some linear functional on the fibers, C, say with respect to T, is you take C and you apply the linear transformation to any old non-zero f in the fiber h sub t. So this f will be in h phi sub t. And then you divide by the norm, sub t, take the absolute value squared, and then you take the sup over all such f. So that's the usual operator norm. So maybe actually let me put a star there to distinguish these two norms. So again, you get a fibration h phi star sub t to omega, and this is also trivial, although it doesn't really matter to us that it's trivial. But the norms again are only quasi-isometric. So what's a section? A section of h phi star. So it's a map. So is a map C from this total space h of phi to C, such that and so for each t in omega, C restricted to h phi sub t is a bounded linear functional. This one is the obvious definition. But what we really want is to know what it means for a section to be holomorphic. So definition. So C in gamma of omega h of phi star, that's the notation for sections, is holomorphic, or for that matter, smooth, measurable, etc. If you take this section C, so let me denote this by C sub t. That's the restriction of C to this fiber. So if you take one of these C sub t, and then you can pair it with F sub t, where F is a holomorphic section of the bundle H. Oops. You take a holomorphic section, you pair this C, and that gives you a function, say from omega into the complex numbers, and this thing should be holomorphic. Is holomorphic, respectively, smooth, measurable, etc. So for all such f. Okay. Now, it's actually just enough to check it for a certain f. So that you can check it actually if you take a single fiber. All the fibers are isomorphic as, not isomorphic, they're actually the same as subspaces of this. So if you pick one of these guys, say in h phi sub 0, then you define a section by just moving it constant. You can move it parallel. Its norm changes, but it's the same vector as you go along. And if you have holomorphicity for all of those, then you will have holomorphicity in general. Okay? That you can think of as a frame if you choose it correct. You choose a Hilbert basis, for instance. So, okay. So far, so good. Okay, let me give some examples. examples of sections. I just gave an example of a section of H. So if you take F in H phi 0 and define so something like, let me call this G actually, G maybe, yeah, phi. Okay. And then we define F of x and t to be just phi of x. And then the corresponding F is holomorphic. Okay, so this is a simple example. Here's a non-example. So let's say, for example, if G is such a holomorphic section, then you can define, let's call it C sub G. So this will be in gamma of omega H of phi star. This will be defined by, so C sub G T acting on, say, F sub T is just the inner product of, say, Ft with Gt. This is the inner product in H phi sub T. So, Hilbert inner product in H phi sub T. Okay, so this is a smooth section, but it's almost never holomorphic. So even if this is a constant section, this typically won't be holomorphic because there's a dependence on of the metric on T as well, the inner product. G sub T is the restriction of G to the fiber at T. Right, so this is a holomorphic section of H of phi, so G sub T is an H phi sub T. Maybe I should have written G of T, but fair enough. Okay. Okay, here's the most interesting example. Okay, so let's choose some point x in capital X, and then we'll also choose some v in the fiber of L over X, okay? Okay, so what I'm going to do is now define, first of all, this map C superscript X. So this is meant to be a linear functional on the fibers, a family of linear functionals on the fibers of this bundle, right? So I have to tell you what it does to a section F in H phi sub T. And what it does is it just evaluates F at X. Okay. So this actually is not a linear functional because this is a point in L sub X. L sub X is isomorphic to C, but the whole problem with vector spaces that don't come with a basis is that there is no canonical isomorphism of that vector space to the standard Euclidean space of the same dimension. So to do that, you need some vector, but it should be non-zero. So I forgot to write that, so non-zero vector. Then you can define maybe eta xt to be, I'll just write it vaguely as 1 over v cxt. It just means that this section f at the point x is some number times this vector v, because v serves as a basis for the fiber. So that's the number I'm going to give. Well, actually, I don't care so much about this one. This is an example. So this is holomorphic. But the truth is that looking at linear functionals is a bias of coordinates. The reality is you should really look at linear transformations to the fibers of L. That's the more natural object. And I'm going to describe this object in more classical terminology now. Okay? So some of you will probably know the answer. So how do you prove? So, this is this claim, but I haven't even proved that it's a bounded linear functional. So first we must show that this, say, Cxt, thought of as a map from, so H phi t to Lx. So Lx is the fiber it's mapping to, but I need to, because it doesn't have a basis, I need to give some inner product on this. So the inner product is just going to be the pointwise evaluation e to the phi t of x, this metric. Okay? So we must show that this is clearly linear, but this linear map is bounded. So the point evaluation should be bounded. What does that mean? It means that f of x squared e to the minus phi t of x should be less than or equal to some constant that quite possibly depends on x times the norm of f squared with respect to t. Okay? So that's what boundedness means. And this inequality is true. Some of you will probably recognize it when there's no weight as the submean value property. It's often called Bergman's inequality. If there's a smooth weight, it's not a big deal, but why don't I leave that as an exercise as well? Sorry? Integration of what? No, it's a number, right? I'm computing the norm of this vector in L sub x with respect to this pointwise metric. So it's just a number. Okay, so now actually the Ries representation theorem applies. So Ries representation theorem implies that there exists some vector, call it kx sub t, in h phi sub t, this Hilbert space, such that xi x t acting on any f is going to be the integral of f kxt bar e to the minus phi t. So maybe I should be a little more concrete here. This is the inner product. So just it's the inner product sub t of f with kxt. Okay, and so in fact, this now we know that this kxt is actually a section of L, but I'm going to define k sub t of x and y to be k y t of x bar. Okay, so this object has a name. This is called the Bergman kernel. So this, in fact, this KT is itself a holomorphic section of the following vector bundle. So it's going to be okay, so let me try to explain this. So this X is a complex manifold. So actually X bar is also a complex manifold. The complex charts on it are Z bar, where Z is a chart for X. Okay? And this L bar is the same complex conjugate manifold, the total space of L, and it gives you a holomorphic line bundle over X bar. It's just taking the complex conjugate. They're diffeomorphic and they have the complex conjugate structure. So then you have maps from X cross X bar, to X. That's what I'm calling pi 1. Pi 2 is to X bar. And I can pull back those two holomorphic line bundles. And this is a section of, this should be tensor, excuse me. It should be the tensor product. It's a tensor product, which means it's a sum of sections of L at X tensor with the complex conjugates of holomorphic sections of L at Y. So that's the kind of object that it is. And in fact, what you can prove, and it will be an exercise later, is that for this thing, the way it's defined, it will be a sum of, so I'll state this as an exercise later. So X and Y, this will be a sum, I going from 1 to infinity, of Gi of X tensor Gi of Y bar, where this Gi is an orthonormal basis for H phi T. So this depends on T somehow, but in a more complicated way. It's not holomorphic in T. Okay? And one of the questions we would like to know is, what is the dependence of this object on T? That's a complicated question. So this goes a little bit back to Gautam's question before. It's how do the orthonormal bases actually change as you go from point to point? So that can be in a very complicated way. And we're going to show later that under certain conditions on the curvature of the metric e to the minus phi, at least this object will be rather well behaved. So for example, the logarithm of kt of x comma x will be plurisubharmonic in T. It's a very strong statement, but we'll appreciate it only later. So. Okay, so this is actually a Bergman kernel you know and love. Some of you love. Okay. Okay, so now I'm finally ready to state Berenson's theorem. Actually, I'm only going to state a special case. So, so assume the metric e to the minus phi for p1 pullback L to x cross omega it satisfies dd bar phi plus the Ricci curvature, well, let me write this correctly, pi pullback of the Ricci curvature of omega is greater than or equal to 0, or maybe bigger than 0. Then the conclusion is, then for every holomorphic section, omega of the dual, the function log norm C. Let me write it like this. Omega containing T going to log square norm of C sub T squared. The square is not important. This is in the dual norm. So this function is plurisubharmonic, or if you have strict positivity, this is strictly plurisubharmonic. That's the statement of Berenson's theorem. So in fact, this theorem automatically implies the statement I made about the plurisubharmonicity of the logarithm of the Bergman kernel. As soon as you verify that this norm is the sup, well, it is equal to k sub t of x comma x. And that will be an exercise later. Okay. Actually, I want to talk a little bit more about the Bergman projection, and then tomorrow I will prove this theorem and get maybe one application. I think a few people here like this Suita conjecture, so it follows almost trivially from this theorem. And so I'll explain that, and that will probably be my final punchline. Okay. Let me say a few words to conclude today about the Bergman projection. Okay. So let me now introduce the non-holomorphic version of the space H of phi. So I'll call it e to the minus L2 of e to the minus phi sub t for not short enough, but short. So this is the set of all f that are just measurable sections of L, such that the integral over f squared e to the minus phi t dv sub g is finite. Okay. So then, of course, this contains the holomorphic guys. And then this inequality here, can be used to prove that this is a closed subspace. This is a closed subspace. So then you have a holomorphic. You have a bounded orthogonal projection. This is the orthogonal projection. And in fact, and this is going to be another exercise, in fact, this PT of some, maybe it won't be an exercise, it's too easy. So PT of such an F, I claim will be the integral over X of f of y, kt of xy, e to the minus phi t of y, dv sub g of y. So it's given by this Bergman kernel, hence the name Bergman kernel, or Bergman projection. Depends which one you want to take first. Okay. So this is just trivialities, but actually what I will need is a link between the Bergman projection and the D-bar equation. D-bar, inhomogeneous Cauchy-Riemann equation. Okay, so let me explain that quickly. So, for example, so assume that you have some U1 and U2 that are both in one of these Hilbert spaces. Doesn't matter what T is, just some fixed, T is fixed in this discussion. And let alpha be an L-valued 0, 1 form such that D bar, U1 and U2 are two solutions of the same D bar equation. Okay? So then, of course, U1 minus U2 is holomorphic. So it's, oops, my bad here. L2 e to the minus phi t, and this is an h phi t. Difference is an h phi t. So in particular, so the solution of minimal norm must be orthogonal to h phi t. Okay? Let's give this guy a name. Okay, so I'll just end with this theorem. So fix t in omega. So if dd bar phi t plus the Ricci of g, Ricci of g is greater than or equal to some theta, and this was some smooth positive 1-1 form, then the integral over x of u minus pt u squared e to the minus phi t dv sub g is less than or equal to the integral over x of d bar u squared computed with respect to theta of e to the minus phi t dv sub g, provided the right-hand side is finite. Okay, so let me just give a quick proof. So suppose you take some u. U automatically solves the equation d bar u equals d bar u. Right? But then if I remove the holomorphic part, so if I project away the holomorphic part of u, then the solution I have is actually the solution of minimal norm. So that's a little argument you have to do. Okay, so that means that this is the smallest possible norm that you have. But on the other hand, under these hypotheses, by Hörmander's theorem, there is some solution whose norm is less than this, provided this is finite. Since this is the smallest one, it must also satisfy this inequality. Okay? So proof. Yeah, right. Yeah, that's the. Let me just repeat that. So clearly, U is a solution of d bar U equals d bar U. That's the hardest part of the argument. Okay. Then U minus PT of U is the smallest solution with respect to our norm, and the Hörmander solution therefore gives an upper bound. For the norm of u minus pt u. And that's the one over there. So it's a really elementary observation, the link between the Bergman kernels and Bergman projections on the one hand, and solutions of minimal norm on the other. So tomorrow we're going to use this to give a proof of this theorem. Today I tried to keep it gentle. Tomorrow there will be some calculations, but it's never going to be as bad as yesterday. And these things are getting better. Okay, you guys have some coffee and I'll put some problems on the board.